An oblique asymptote, sometimes called a slant asymptote, is an asymptote that is neither horizontal nor vertical, in other words, diagonal. So what a slant asymptote is if f of x equals a polynomial function, well, let's say a of x over b of x, and they're polynomial functions with no common factors other than 1, and b of x does not equal 0 because we can't have b of x be 0 because that's the bottom of the fraction, then f of x has an oblique asymptote if the degree of a of x minus the degree of b of x equals 1. In other words, on that, if the numerator's degree is exactly 1 higher than the denominator, then it will have this oblique or slant asymptote. The equation of the asymptote is found by dividing the numerator by the denominator and ignore the remainder. So, to find a graph with an oblique asymptote, we're going to graph f of x equals x squared plus 4x plus 4 over 2x minus 1. So, we'll still go through the steps of, is there a vertical asymptote? And yes, there is. There is a vertical asymptote because when you set the denominator equal to 0, you get 2x equal to positive 1, and so there is a vertical asymptote at x equals 1/2, so I'll go ahead and draw that in. Is there a horizontal asymptote? No, there is not, because for horizontal asymptote, the numerator cannot be larger than the denominator. Notice the numerator is a 2, and the degree of the denominator is 1. It's that 1 next to the x, so there is not a horizontal asymptote. However, since the numerator's degree is exactly 1 higher than that of the denominator, there will be a slant or an oblique asymptote. So we need to find the equation of the slant asymptote by dividing the numerator by the denominator through long division. So we will have x squared plus 4x plus 4 all over 2x minus 1, or all divided by 2x minus 1. And remember, the key term is the 2x. So how many times does 2x go into x squared? Well, it goes in there half x times. And we know it's a half x because a half x times 2x is x squared. We also have to take a half x times negative 1, and that is negative half x. And then we subtract, but we're going to subtract the algebra way, which involves changing the signs and adding. So the x squares will cancel out. 4x plus a half x, that is 9 halves x. And then we bring down the plus 4, and we do it again. So 2x times what is 9 halves x? Well, they both have an x, so the answer is just going to be a number. So 2 times what is 9 halves? And that's going to be 9/4. And if you have trouble thinking how that's figured out, think about this. I just said 2 times what would equal 9 halves. Well, how can you figure out what that question mark is? Well, you can just divide both sides by 2, and that mystery is going to be 9/4, because 9 halves divided by 2 is 9/4. So 9/4 times 2x, we already know that's 9 halves x. And then 9/4 times negative 1 is negative 9/4. We are going to subtract the algebra way by changing the signs and adding. Those cancel. And 4 plus 9/4 is going to be 25/4 for a remainder, but that's really not important for our purposes here. What's important is that we have the equation of the slant asymptote, which is right here, 1/2 x plus 9/4. So I will go up to 9/4. That's about 2.25. Place a point there. And then from that point, I'll go up 1 and over 2, up 1 and over 2, and so on. And here's my slant asymptote, right through here. Okay, now that we have our asymptotes, we're going to go ahead and do a t-chart. So we'll pick some points that are close to the vertical asymptote. So on the right side, good points would be 1, 2, and 3. On the left side, we would have good points at 0, negative 1, and negative 2. So we're going to plug those back into the original problem. So let's say for 1, that would be 1 squared plus 4 times 1 plus 4, and all of that is over 2 times 1, and then minus 1. So 1 squared plus 4 times 1 times 4, that's going to be 9 over 2 times 1 minus 1 is 1, so that is going to equal 9. And then we do it again for 2's. So I replace all those 1's, that's what x's are. I'm going to just put a 2 over the top of those. And then what's that going to equal? Well, that's going to be 2 squared, which is 4, plus 4 times 2 is 8, plus 4, all over 3. So that would be 16 thirds. And then when we do the rest of the problem by plugging in 3, 0, -1, and -2, then we get these answers. And there you go. So let's graph those. So we have 1, 9, that's way up here. 2, 16 thirds, that's about 5 1/3. 3, 5, it's about right here. 0, -4. -1, -1/3. About right there. And then -2, 0. So I do think we have enough to figure out where these graphs are, because we know that they're not going to cross either the vertical asymptote or the slant asymptote as we approach infinity. So it looks like the graphs are starting to turn down here, and then they will go out next to the slant asymptote on that side, and the same down here. It'll come in, looks like it's turning in this area, and then head out to the slant asymptote that side. So there's what your graph looks like. Down here, I'm not going to show this full example because, as you already know, it takes a while to do so, but I do want to point out that since this does have a slant asymptote, since the degree of the numerator is exactly 1 higher than that of the denominator, when I do my long division, I have 4x to the 3rd power, but I do have to put in a 0x squared plus 0x minus 1 because I am missing some terms after the x cubed. And that also is true if you're missing any terms in the denominator. This one does not miss any terms, so I can just go ahead and write it out as is. But remember that you do have to write all the terms of x in descending order of exponents before you divide. So, knowing what we know so far about asymptotes, what could you predict about this equation? X squared minus 16 over x minus 4. So what we know about asymptotes is that it looks like that this would have a vertical asymptote at x equals 4, because that's what would make the denominator equal to 0. And it looks like we should have a slant asymptote too. We would have to divide the numerator by the denominator, because it looks like that because the numerator is exactly 1 higher than the denominator. But when I graph that on a graphing utility, this is what I come up with. And it appears to be a straight line. Even if I zoom out, it appears to be a straight line. So what happened? Why am I getting a straight line in something that looks like it should have asymptotes? And the reason for that is that this is not simplified. This equation is not simplified. X squared minus 16 over x minus 4, thinking back to last chapter, can be simplified if we factor out the x squared minus 16 to x, and it's x plus 4 and x minus 4. And that the x minus 4's would eliminate each other, which means simplified, this equation is just f of x equals the linear equation x plus 4 with a y-intercept of 4 and a slope of 1. So there you can see in the graph, that's what I have. I have a y-intercept of 4, and I do have a slope of 1. So y-intercept of 4 right here. See how it locks in with the 4. And then I have a slope of 1, so it keeps going up 1 and over 1, up 1 and over 1, up 1 and over 1, and so on and so forth as we go through it. Wait, what happened there? I got a weird flash of some kind. It went down, 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 and then suddenly, did you see that? Right there. See if I can lock it in. See, I got like a circle there where it says 4 undefined. Well, why do I have that? Why is there a circle suddenly in the middle of my linear equation and at the point of 4, and then it says undefined? And the reason is because we go back to the original problem. The original problem said that we cannot have 0 in the denominator, and that happens when x equals 4. Normally we would consider that an asymptote. We already know that this is a straight line and it doesn't have an asymptote. However, the denominator still can't equal 0. So x cannot equal 4, and that is why we have a hole in the graph right there. Because if x does equal 4, that means I can't plug 4 into the original problem because that would give me 0 in the denominator. So we get a new type of discontinuity. So instead of an asymptote, we have what is called point discontinuity. In some cases, graphs of rational functions may have a point discontinuity which looks like a hole in the graph. This is because the function is undefined at that point. So you can see at this key concept that it says if f of x equals a of x over b of x, and there is a factor of both a and b. So in the case of up here, that factor was x minus 4, was able to cancel out part of the numerator and the denominator. Then there is a point discontinuity at x equals c. In other words, wherever the denominator equals 0. So let's practice a graph with point discontinuity. So we have f of x equals x squared plus 4x minus 5 over x plus 5. So before we try to find any asymptotes, which has been the first step so far, we better check to make sure that this graph is simplified. And it is not, because the numerator can be factored into x plus 5 and x minus 1. And the x plus 5s would cancel, leaving us with the simplified version. It's just x minus 1. So since it's x minus 1, I would go down to negative 1, place a point there. My slope is 1, so up 1 over 1, up 1 over 1. And I would draw my straight line. Right through there. However, we do have to take into account that it is still a rational function and we still can't have 0 in the denominator. And so that means x cannot equal negative 5, because if x equals negative 5, that would place a 0 in the denominator. So I have to go back to my graph, and I need to go over to where the x equals 5. So if I go over to where the x equals, negative 5. If I go over where the x equals negative 5 and down, right through there, I do need to place a hole in the graph right about here where x equals 5. So I'll go and I'll draw a little circle there to represent where x equals negative 5. I think I said 5 a while ago, where x equals negative 5. And there is my point discontinuity.